Okay, so first I will do a small summary of what we did last time. Okay, so we derived together the Bernoulli equation, and we have seen that it can be written in several forms. One of the forms is the following one: P over rho plus V square over 2 plus Gz equal to constant. And P over rho term is associated with flow energy. V square over 2 is associated with kinetic energy. And Gz is associated with potential energy. Okay? And we can then say when Bernoulli equation is applicable, it's similar to the conservation of mechanical energy in dynamics. Now, the different forms of Bernoulli equation. This is the first one. Just you should pay attention that all your terms have same dimension. So if you use P over rho, you should have V square over 2 and you should have Gz. And all of these terms then will have as unit meter square per second square. Another possibility is to write it in the following form. So if you multiply all terms by rho, then you get P plus half rho V square plus gamma Z equal to constant. And then all your terms will have the unit of pressure, which is Newton per meter square. And we consider that this is the static pressure, this is the dynamic pressure, this is the hydrostatic pressure, and it should be equal to the total pressure. So this constant will be equal to the total pressure. Now, another way to write it is to divide this equation by gamma. Then all your terms will have as unit meters, and we call this term pressure head, this term velocity head, and this is the elevation head. Okay, so you are free to use any of these three. Just be consistent with units. Now, what is static pressure, dynamic pressure, and hydrostatic pressure? When we talk about the static pressure, this is the static pressure, and it just represents the pressure of the fluid without considering any dynamics effect. So this is the pressure measured by a manometer, okay, irrespective of the velocity of the flow. While this term is called the dynamic pressure, okay, and it represents it's physically, if you want, it represents the pressure rise when the fluid in motion is brought to a stop isentropically. What do we mean by this? So if you consider, let's say, that you have a fluid flow and you neglect any change in elevation going from 1 to 2, okay? If it's characterized by a certain static pressure and a velocity v, if you force your fluid to decelerate to 0, then without losing energy, this is why they say to stop isentropically, this means without losing energy, then all your flow energy, which is represented by this term, will be all the energy will become a flow energy, because the dynamic energy will be transformed into a flow energy. So the velocity will decrease and the pressure will increase. So we say then that this term represents the dynamic pressure, which corresponds to the rise of possible pressure in the flow, because I'm able to rise pressure of my flow by reducing the velocity, and the maximum reduction will be to have a velocity of 0, which will correspond to P maximum, and this maximum pressure is then equivalent to the static pressure plus the dynamic pressure. So we define the dynamic pressure as the pressure rise when the fluid is brought to a stop without losing any energy. And finally, and of course here, if you want, just you can add a note at negligible change in elevation. So if I don't consider elevation change, okay, at negligible change, because if the elevation change, it will also affect the variation of our terms, because as you can see here, P plus rho V square over 2 plus rho Gz is the constant. Okay. Now, for the hydrostatic pressure, the hydrostatic pressure is represented by this term, rho Gz. So if I change in elevation, I have a change in this term. Okay, and as we have conservation of energy when we apply Bernoulli, if this term decreases, this means that the summation of these two will increase. So it depends on the scenario. You can have hydrostatic energy that can be or potential energy can be transformed into or kinetic energy or flow energy or both. Okay, so it depends on the case. So we can say then that this term is the total pressure, and the total pressure, P total, is equal to the summation of static pressure plus dynamic pressure plus hydrostatic pressure. And sometimes we term these two together, okay? This is called the stagnation pressure. The summation of static and dynamic is called stagnation pressure. So here, again, we'll define what is the stagnation point. So whenever we consider a flow, you have streamlines. So when you want to visualize a flow, you can end up with several streamlines. Okay. So for example, here, if you have a flow over this ball, you will have like symmetry because of the symmetry in the object geometry. So you will have the following case. You will have streamlines that will go under the ball, others that will go above the ball, and you have one streamline called stagnation streamline, which will end up here with a velocity of 0. And this is called the stagnation point, where I will have then here the maximum pressure, because all kinetic energy will be transformed into flow energy. Okay. Now, what is the concept of a pitot tube? Okay, pitot tubes are used to measure velocity of a flow. So how we can use Bernoulli equation to measure the velocity of a flow? This is the application. So if you consider the following case, you have a flow moving in a duct at a certain velocity v, and you want to measure this velocity. Okay. To do this, you can use the following device. So first, in this device, you have first this manometer, okay, will be able to give you the static pressure, because as your flow is moving, you can measure here at this point what is the pressure of your flow. This can be measured through the elevation of this column, the height of this column. Okay. Now, what you will do in the pitot tube is that your flow, as it moves through your pitot tube, will decelerate until reaching here a velocity of 0. But your pitot tube is constructed in a way to decelerate your fluid without losing energy. So this is what we call, it's brought to rest isentropically. Okay, so at this point the velocity is equal to 0. And this is why the pressure measured at this point, the static pressure here, is the stagnation pressure. So the pressure that I will measure here is the stagnation pressure, and will be larger than the static pressure here. Why? Because all kinetic energy was transformed at this point to flow energy, because I don't have change in elevation. So now, as you can see, the height of your column is much larger than the height here. And you can say that the difference between these two heights represents the dynamic pressure. Because if I apply Bernoulli equation between these 2 points, the elevation is not changing. Okay. If I call this point 1 and I call this point 2, I can write the following. I can write that P1 plus rho V square over 2 plus rho V1 square over 2 plus rho GZ 1 equals to P2 plus rho V2 square over 2 plus rho G Z2. Okay. Now, first, since I don't have a change in elevation, I can simplify these two terms. Now, since my fluid is brought to rest at point 2. This velocity term will cancel out. Now, I will have the following final result. P1 plus rho V1 square over 2 is equal to P2. And P2 is called the stagnation pressure because it corresponds to a velocity of 0. So I can deduce that the stagnation can be written as P plus rho V square over 2. And since I am interested into calculating the velocity of my flow, if I rearrange terms, I can get the expression of my velocity. So V is radical of 2 delta P over rho, where delta P is P stagnation minus P. So it's P at point 2 minus P at point 1. And as you can see here, delta P is represented by this height. Okay, so it's if you know the, of course you will know the nature of your liquid here. So this delta P will correspond to gamma times H, delta H, between the two tubes here. So you can consider that gamma delta H will give you a measurement of rho V square over 2. So this will allow you, so you can replace here in this equation P stagnation minus P by gamma delta H, and then you will be able to measure your velocity. This is very used in labs. So hopefully if you will take the fluid mechanics lab, you will you will use pitot tubes, and you will see how you can measure the velocity of a flow using this device. Okay. Any question on this? So now to summarize again, as a summary, Bernoulli equation requires the following condition to be applied. My flow should be steady. My flow should be frictionless, because I should not have losses, okay, to be able to apply Bernoulli equation. I should not have a shaft work, so I cannot apply Bernoulli within a turbine or a pump, because if I have a fan or a shaft, this will destroy my streamlines, and this will lead to certain interaction with the environment. So I can have loss of energy or gain of energy. So I cannot apply the Bernoulli equation. I should have, we have seen together the general Bernoulli equations that can be used for incompressible flows, but in general we deal with incompressible flows. So rho is constant, so no need to keep it, because if it's the general one, you should do integral P over rho if rho is varying with pressure. Okay, but in general, when we deal with incompressible flows, then rho is not varying, so I can take it outside of the integral, and this will give me a much easier result. So then integral of dp over rho will be just p over rho. And concerning the fifth assumption, I should not have heat transfer, do not have losses of energy, and finally, my flow should be along a streamline. Okay. Now, for incompressible flows, this will not be applicable only for liquids. You can apply it sometimes for gases. Just you have this restriction. You can consider a gas to be treated as incompressible if the Mach number is less than 0.3. And to remind you, the Mach number is equal to the velocity of the fluid over the speed of sound in the fluid, okay, in the same fluid. So just pay attention for this. It should be the velocity of the fluid over the speed sound in this fluid. If this number is smaller than 0.3, then it's fine. You can treat the flow as incompressible. If not, you should have a relation between rho and pressure to be able to apply the general Bernoulli equation. Okay, and the final assumption that is very important is that the 2 points where you are applying Bernoulli should be along a streamline. So if you consider, let's say, if you consider a nozzle, for example, and you have streamlines of the flow, okay, if you consider the symmetry line, you can consider any 2 points, 1 and 2. So since these 2 points belong to the same streamline, you can apply Bernoulli between 1 and 2. But you cannot consider a point here, point 3, on another streamline and say, I want to apply Bernoulli between 1 and 3. And of course, to satisfy the conditions, you should be, to not have any friction, you should be far away from walls. So in general, always we try to deal with streamlines at the center of the device to be far from walls and to not have friction effects or viscous effects. Okay, so now let us consider several examples using Bernoulli equation. These are widely used examples. So the first one will consider a reservoir of water, and we are interested into calculating the discharge velocity function of the height of water in my tank. Okay, if I want to apply Bernoulli equation here, I should use a streamline. As we said, we select a streamline that is far from walls to neglect any frictional effect. So I can consider the following streamline between points 1 and 2. So if I start from point 1, I should know the following property, P1, V1, and D1. So P1 over rho G plus D1 square over 2G plus D1 equals to, at point 2, P2 over rho G plus V2 square over 2G plus Z2. Now, how we can simplify? First, points 1 and 2 are both exposed to the atmosphere. So I can consider that P1 is equal to P2. This is why I can cancel out these two terms. Okay? Now, always when you have two terms, you can see if one is negligible compared to the other. Because if V1, for example, is much smaller than V2, you can neglect it compared to it. This is the case here. Why? Because here, due to conservation of mass, okay, the velocity of water that is going down can be related to the velocity that is exiting by applying the continuity of mass. So I can write that m dot 1 is equal to m dot 2. Okay, so I have rho times a1 v1 is equal to rho times a2 v2. And since it's an incompressible fluid, rho will cancel out. So I can say that a1 v1 is equal to a2 v2. And because, as you can see in the figure, a1 is much larger than a2. So a1 very large compared to a2. Then I can say that v1 is much smaller compared to v2. So I can consider that this term is negligible compared to v2 square over 2g. So I end up with a very simple result, which tells me that z1 equals to v2 square over 2g plus z2. Now, whenever I consider z, I should take a reference. So here the easiest reference will be to take it at level 2. In this way, z2 will be equal to 0. So what can I deduce? And this is a very physical result. I have that z1 is v2 square over 2g. So higher is the water height in the reservoir, larger will be the discharge velocity. And this is expected because in this case, I will have larger potential energy, okay, that is transforming to, at this point, kinetic energy, okay? So the potential energy at point 2 is 0, okay, while the kinetic energy is very large, as opposed to point 1. At point 1, the kinetic energy is nearly 0, while the potential energy is considerably large. So from 1 to 2, we have transformation of potential energy into kinetic energy. Another example, if I consider a tube containing water at a certain pressure and it was closed first, okay, then I removed my sump a little bit, so I just opened a very small area so that water can exit the jet. And my purpose is, can exit the pipe, and my purpose is to determine, if I do this, what will be the maximum height reached by the jet. Okay, this is the question. So first, I can say that Bernoulli equation is applicable, but I should be far from walls. So I can consider a streamline just passing by the center of this area like this. okay? And I can consider any point 1 here in the flow at this level, and my point of interest, which is the maximum height reached, I will call it, it will correspond to point 2, okay? And now if I write my analysis, I have at point 1, so here, since you opened a very small area here, this means that the velocity in your duct is nearly zero. Why? Because if you opened a very small area here, using the same concept of the reservoir, okay, at this level you have a much larger area. So V1 is very small compared to the velocity of jet exiting your tube. So you can consider that V1 within the pipe here is nearly equal to zero, okay? And you have P1 is the pressure of your flow inside the duct. And of course, larger is the pressure of the flow inside your duct, then larger will be the height that the water jet will reach, because the flow energy will be transformed to potential energy. So this term represents the flow energy of the water in your tube. We said that we can neglect the kinetic energy here because the cross section here is much larger than this one. We can consider that Z1 represents the reference. So Z1 is 0. I will take the reference of Z here. And then for the other term, the point 2 is exposed to the atmosphere. So I can say that P2 equal to P atmospheric. Now, since I am interested in the maximum height reached, Z2, then I have that at this level, V is 0, because at the maximum height, the velocity reached is 0, so V2 is 0, plus Z2. From this relation, I can say that P1 over rho G is equal, after simplification, is equal to P atmospheric over rho G plus Z2. So I can deduce, so if you take P atmospheric to the other side, then P1 gauge, which is the difference between the absolute pressure and P atmospheric, over rho G, is equal to Z2. And as we said, physically it's expected because the flow energy will be transformed to potential energy. Okay. Another example on Bernoulli that we are using a lot these days is the siphoning effect. So if you want to have fuel in your can, and you want to take fuel or gas from your tank, the tank of your car, you can use this system. So this system consists on the following. Your gas tank should be at an elevation higher than your gas can. In this way, okay, you can drive flow from point 1 to point 2, okay? And in general, what we do, we use a long tube. We put it in this way, so flow will go up and then down to reach our gas can, okay? Now, what is the idea here? I can apply Bernoulli in this problem between several points. I can apply Bernoulli equation. So first I should consider a streamline. I can consider the streamline from the free surface here. So this is the streamline I will consider. My streamline will go over the tube. And here it will end up at this point. I have three main points of interest here. The first point is point 1, which is the surface of my gas tank. The second point corresponds to the maximum height reached here, and or this is point 3 as I call it, and the third point is point 2, is at the gas can level. Okay. Now, if I want to apply first between points 1 and 2, if I want to apply between points 1 and 2 the Bernoulli equation, what do I? First, you have that the pressure here, okay, is equal to P atmospheric, because here you have air at atmospheric pressure, okay? And also in your gas can, it's exposed to atmosphere, so P here is equal to P atmospheric. This is why P1 over rho G and P2 over rho G will cancel out, okay? Now, Concerning V1 and V2, so since these velocities correspond to large areas, so whenever you have a large area, you can consider that the velocity, so here's the velocity value at this level, the area here is much larger than the velocity here at this point, okay? Because point 2 is just at the exit of your tube. So you are considering this point. So you are exiting to the gas can where P atmospheric is governing. So P2 is equal to P atmospheric, and V2 corresponds to the exit velocity. And since this area 2 is much smaller than A1, so since A2 is much smaller than A1, then you can say here also that V2 is much larger than V1. So the velocity, this term, is negligible compared to this one. So I can consider it as 0. Okay. Now I have the elevation of point 1, Z1. And we consider that the reference here, Z2 is the reference, so Z2 equal to 0. So we end up with Z1 equal to P2 squared over 2G. So the main condition to be able to produce a siphoning effect, okay, is to have 2 at a lower level than 1, because this difference in height is the driving for flow in the tube. Now, we should pay attention here, okay? Point 3 is a critical point. Do you have an idea why point 3 is a critical point? Okay, let us do together the analysis. We will see together, okay, that the pressure at point 3 is a minimal pressure. And because it's minimal, then we can have cavitation. What is cavitation? I will remind you of cavitation. If you remember, when we considered chapter 1, we talked about a property of a fluid. So any liquid, if you consider a certain temperature T, okay? So if I consider a certain temperature T, I have a drop in pressure. If I continue to decrease pressure, I will reach a certain pressure called cavitation pressure, where I will see the formation of bubbles in my liquid system. This means that I will have conversion from liquid phase to vapor phase. Okay, so this is why this phenomena is not desired a lot, because I will have formation of bubbles in my liquid. So I should avoid to go below the cavitation pressure. And always in a fluid system, I should determine what is the minimum pressure in my system to make sure that P minimum is larger than P cavitation, so I can make sure that no possibility for cavitation crosses. Why here point 3 will correspond to the minimal pressure? Because as you go, when you move from this point here, as you move up, what is happening? As you move up, if you apply Bernoulli equation, okay, you have that since you have the same cross section in the tube, and you have a conservation of mass, so you have the flow rate is constant through your tube. This means that the velocity V is the same. So if I consider here any cross section, I have the same velocity along the streamline. Okay, so if I apply between any points in the tube, the velocity term will remain the same. So what do I have then? I will have exchange between the flow energy and the potential energy. And as I move up, my potential energy is increasing, while my the flow energy is reduced. This means that the minimum pressure will correspond to the maximum elevation. So point 3 will correspond to maximum potential energy, okay, and minimum flow energy. And since the flow energy is minimal at point 3, this means that the pressure is minimal at this point. And this is what interests me. I should make sure that this pressure is not below cavitational pressure to make sure that no cavitation will take place. So this is why we are interested in general to know what is the pressure at this point. So if I want to calculate it, I can apply Bernoulli equation between points 2 and 3, because at point 2 I know properties, I know the pressure, since my jet is exiting to the atmosphere. So P2 can be replaced by P atmospheric. And since V2 is equal to V3, why V2 equal to V3? Because as we said, it's the velocity along the same cross section. So I have a tube of constant cross section. So due to continuity, the velocity at 3 is equal to the velocity at point 2. So these two terms will cancel out. Now concerning the elevation, Z2 is 0 because I am at the reference, and I have Z3 is the height of point 3. So after simplifying terms, I get the following relation, that P atmospheric over rho G is equal to P3 over rho G plus Z3. So as you can see, pressure at point 3 is smaller than the atmospherical pressure, okay? And I should pay attention, I cannot go below a certain stage, because if I drop below the cavitation pressure, I will have formation of box. Okay? Any question on this?
دكتور
Yes, Hassan.
يعني ليش الماس flow rate between the gas tank والتيوب is equal؟
لأنه أنت إذا عندك tube of constant cross section، okay؟ عندك steady application. يعني if you consider a steady application, you cannot have accumulation of fluid. You have a liquid هون صح؟ فكل شيء بفوت. يعني if you consider any cross section, what is getting in should get out from the other side. So if you consider any section of your tube, you have that m dot in should be equal to m dot out. Okay, and what is the expression of the mass flow rate? It's rho times A times V. Okay, and since rho 1 at any 2 points, so here for example you can apply between 3 and 2. So if you apply between 3 and 2, you have rho is constant because it's a fluid, it's a liquid. So rho A2 V2 equal to rho A3 V3. And since you have constant cross section here for your tube, you don't have variable area, then A2 is equal to A3. And as we said, it's incompressible, so rho is the same. So you end up with V2 equals to V3. Okay?
Yes.
Okay. Any other question on this?
دكتور
Yes?
نحن ليه ما اخذنا بس 1 ل 3 اخذنا نحن 2 and 3
Okay. You can apply between 1 and 3. It's not wrong. You can apply Bernoulli or between 1 and 3, or between 1 and 2, or between 2 and 3. And you have the freedom to apply between any 2 points على streamline. Okay? نحن أول شيء when we applied between 1 and 2 طلعنا الvelocity. يعني حسب what is your purpose. If your purpose is to get the velocity of your flow V, then you apply between 1 and 2. If your purpose is to get an expression for P3, okay, you can apply directly between 2 and 3. هلا if you apply between من الأول من 1 ل 3 بيكون عندك 2 unknowns اللي هن ال P3 وال V3. So since it's one equation, 2 unknowns, you still need another equation. So مجبور تعمل 2 Bernoulli's equation to get your 2 unknowns اللي هن ال velocity of the flow and the value of pressure at point 3.
يس هلا هون البوينت 1 اللي عم ناخذها هي بالتيوب موجوده.
البوينت 1 هي على السيرفيس للريزرفوار. Why we considered 1؟ لأنه بنعرف ب1 إنه ال velocity is negligible، وبنعرف إنه it's exposed to atmosphere, so we know that the pressure is equal to the atmospherical pressure. Always you try to select points where you know a lot of information. يعني إذا باخد point هون مثلا من الأول ما بعرف عنه شيء. If I take a point here, I don't know the velocity, I don't know the pressure. So this is why I try to use points where I know something. And here, at this level, I know that P is P atmospheric. I know that the velocity is very small because the area is large. So this is why it's good to consider this point. And for the exit point, also I know information that it's exiting to the atmosphere. So I know the pressure here. So always I try to select points of known properties to reduce the number of unknowns. Okay?
Yes, thank you, Doctor.
Welcome. Any other question on this?
دكتور
Yes.
بس كرمال الجاس تانك الاريا تبعها is larger than the area of the tube.
Okay. بالجاز
بس
كان حسن ما عم ناخد هيدا الليفل. فيك تاخد هيدا الليفل ساعتها معك حق. هن عم ياخدوا just exit here. You know why they do this؟ لأنه هن بدهم يجيبوا ال velocity of the flow بقلب الضغط. إذا أنت بتاخد ال 2 at this level ما بيطلع لك as unknown ال velocity of the flow. Okay? So you will not be able to find it. لأنه هون ال velocity مثل ما أنت قلت is small لأنه ال area is large. Okay? Since you are interested into knowing what is the velocity of the flow in your tube, the point 2 منه here, it's just here at the exit of the tube.
yes doctor, thank you.
Okay, well. Okay, now an example of velocity measurement by a pitot tube. So this is the concept we talked about before. Here we have a numerical example. So if you have a flow and you want to measure its velocity, use the pitot tube device. So you have water flowing from points 1 to 2. So at point 1, you have a certain velocity V of the flow that you want to measure. Now, what will happen at point 2 is that a part of your fluid will move through the pitot tube and it will be brought to rest in an isentropic way. So the velocity at point 2 can be considered to be 0. Okay. And therefore, if I apply between 1 and 2 Bernoulli equation, I can write the following. At point 1, I have the pressure of the flow that, let's say, I don't know its value. Okay. And I don't know the value of velocity V1. I want to measure it. Plus Z1 equals to P2. Also for P2, I don't know the value, but it's measured using the pitot tube over rho G plus V2 square over 2G. Now for the, whenever you enter the pitot tube, you can consider that your fluid will be brought to rest. So V2 is 0 plus Z2. Now, since you are considering 2 points at the same elevation, Z1 and Z2 will cancel out. And you will end up with V1 square over 2G equal to delta P over rho G. So just here you care for delta P. You don't care for individual values of P1 and P2. You can get individual values of P1 and P2 because they gave you the height. So here you have H1 plus H2. So you have in total 10 centimeters and your fluid is water. So you can say that P1 is equal. And if you know here that you have the atmosphere, let's say P atmospheric. So you can say that P1 is equal to P atmospheric plus gamma times 10 times 10 to the power minus 2. Okay. And for point 2, the pressure corresponds to the height of this column, which is 3